maybe you've heard previous talks, or there are definitely people you can ask questions to other than me as well. Okay, so I want to begin, okay, so I want to begin talking about one of the main objects in complex algebraic geometry. So these are going to be projective varieties. So you can think of a projective variety as some closed subset of complex projective space that's the zero locus of some homogeneous polynomials in n+1 variables. So here we have polynomials fi, and we're just looking at where these polynomials vanish in complex projective space. So some examples of these types of objects, the first, or I guess the easiest examples would be hypersurfaces, when you just have one polynomial and you look at the locus where that one polynomial vanishes. So in this picture, I have x cubed plus y cubed plus z cubed plus w cubed equals 0. And I'm graphing the real points of this 0 locus on one of the charts of projective space. And some other examples come from complex geometry. So it turns out, by a theorem of Chow, that any complex manifold that's, I guess, holomorphically embedded in projective space is a projective variety. So what I want to be talking about is moduli theory in algebraic geometry. So the idea is that we'd like to look at all algebraic varieties of a certain type and try to find some space that parametrizes them. And maybe show that that space has some nice properties. So if you want to look at moduli theory, the first example that you should look at is going to be algebraic curves. So an algebraic curve is just a smooth projective variety of complex dimension 1. And if you think about one of these smooth projective varieties, they're just essentially going to be the same as complex manifolds in projective space. And these objects that I'm talking about are, in the dimension 1 case, are in bijection with compact Riemann surfaces. So if you have a Riemann surface, you can think about the underlying real manifold, and you can think about what its genus is. And if you look at algebraic curves of genus 0, these are just going to be of the form CP1, so the projective line. If the curve has genus 1, then you're going to get what you have, what is called an elliptic curve. And we know topologically this is just going to be one of these donuts. And from complex differential geometry, we know that these all are the form, the complex numbers mod some two-dimensional lattice. And if you have a curve of genus G greater than 1, then you have a similar kind of statement. It's a little more subtle, but these can be written as the upper half plane mod some discrete subgroup of PSL2R with some conditions on the action. So you can try to parameterize curves and find some shape that's going to parameterize your curves. And there's a lot of literature on this subject. So it's a well-known result in algebraic geometry and goes back even before algebraic geometry, that there exists an algebraic variety, which we didn't call MG, that's going to parameterize curves of fixed genus G when G is greater than 1. So you can think about this as some space, and the points in the space correspond to genus G algebraic curves. And as you vary the point on MG, you're kind of varying the algebraic curve, or if you want to think about it as a Riemann surface, you're varying the Riemann surface up to isomorphism. And another thing in algebraic geometry, it turns out that this moduli space MG, it admits a natural compactification called MG bar, which is actually going to be some projective variety. And this is using an approach due to Deline and Mumford, but I won't talk about it here. Any questions up to this point? So this is essentially the theory in dimension 1 for curves. And there's I guess, a very rich literature on MG. And there's a lot of, I guess there's very interesting geometry and interesting things you can say about these varieties. But what I want to talk about now is what you can say for higher dimensional varieties. So for higher dimensional varieties, you need to replace the genus with some other invariants. So what I'll say about this is if you have a smooth complex projective variety, we can associate its Chern class, which is some cohomology class. So if you're familiar with Chern classes of line bundles or vector bundles, this is just the first Chern class of, I guess, the top wedge power of the tangent bundle. And for these Chern classes, it turns out there's some notion of positivity. And I won't define it rigorously, but I'll say what it is in some examples. So we say that our smooth projective variety X is going to be Fano if this first Chern class is positive, Calabi-Yau if it's equal to 0, and the variety is canonically polarized if this first Chern class is negative. So you can think about these three classes of varieties as the kind of building blocks of varieties in higher dimensions. So not all varieties are going to take this form, but roughly speaking, according to birational geometry, these kind of make them up in some imprecise way. So if you want to look at some examples, so previously we talked about algebraic curves, which are characterized by their genus. So an algebraic curve is going to be Fano, or this Chern class is positive if the genus is 0. Calabi-Yau, if the genus is 1, we have an elliptic curve. And then canonically polarized if the genus is greater than 2. And you can also talk about the positivity of this Chern class for hypersurfaces as well. So for hypersurfaces, let's say I have some hypersurfaces which is cut out by a degree D polynomial in a complex projective space. And essentially, the positivity or negativity of the Chern class is determined by the difference between n+1 and the degree of that polynomial. So the Fano case is that the degree is less than n+1. And if you think about the example that I had on the first slide, that means that algebraic variety that I had graphed was actually going to be a Fano variety because the degree was 3 and it was living inside of CP3. Okay. So now one can ask, do there exist nice moduli spaces of higher dimensional algebraic varieties? So it turns out the answer is yes in certain cases. So for canonically polarized varieties, one of those three classes I discussed before, there exist nice moduli spaces parametrizing those objects. So you get some algebraic variety and its points are going to correspond to canonically polarized varieties with some fixed invariance. And it turns out as well, similar to the story for MG, these moduli spaces have a natural compactification via an approach due to Kolar, Shepard, Barron, and Alexiev. And these compactifications are actually going to be projective varieties as well. So I'm not citing the people that this statement is due to because this is a very hard result that relies on many results, especially in birational geometry. So the downside of these constructions over here is these moduli spaces are often extremely hard to construct and describe explicitly, especially if you want to understand the compactifications. So what I want to talk about in this class, So in this talk are Fano varieties, which were one of the three classes I mentioned before. So it turns out it's well known that to algebraic geometers that Fano varieties do not have a nice moduli theory in general. And there are some technical issues to why this is the case. But one of the key issues is that if you want to naively construct moduli spaces of Fano varieties, your moduli space, depending on what you mean by construct it naively, would in general not be Hausdorff. So let me say what I mean by this. So the point is, there exist families of Fano varieties over a pointed curve, and let's call these families x to c and x prime to c, so that over c minus the point, sorry, there's a word missing, the families are isomorphic, but the fibers over 0 are not isomorphic. So what you can think of this, an example like this, as saying that you can think about this as a map or a family X to C is going to give you a map from that curve to your moduli space. And roughly speaking, the idea is that the limit of the fiber xt as t goes to 0 is not unique, because one family, the limit gives you x0, and the other family gives you this other fiber x prime 0, which aren't the same. So this causes a problem, and I think for many years, algebraic geometers didn't really understand what should be the kind of canonical way to construct moduli spaces of Fano varieties. So one solution to this problem comes from differential geometry, and especially from some differential geometers that have or do currently work at Stony Brook. So the idea is that we should really be trying to parameterize not all Fano varieties, but Fano varieties that admit certain nice metrics on them. And the idea is, if you have these varieties that emit canonical metrics, when you construct a moduli space, you should think about, as you vary the point and you vary the Fano variety that you're parameterizing, you're kind of varying these metrics in a nice way. So it turns out the natural class of metrics to look at are going to be Kähler-Einstein metrics. So let me kind of roughly say what these are. So a Kähler-Einstein metric on a complex manifold is going to be a Hermitian metric, which you can think of as the kind of natural cousin of Riemannian metrics that are the natural class to look at on complex manifolds rather than real manifolds. And it's going to satisfy two conditions. So it's Kähler, meaning this metric, Hermitian metric, corresponds to a 1-1 form that's closed. And then it also satisfies the Einstein equation, which says that this notion called the Ricci curvature of the 1-1 form is a scalar multiple of the original 1-1 form. And what's amazing about these types of metrics is that when they exist, they satisfy certain uniqueness properties. So the existence of these metrics give you the answer of whether or not algebraic varieties admit kind of canonical metrics. So now that we know that they have these nice uniqueness properties, you can ask whether or not these metrics always exist. And it turns out that these metrics always exist on canonically polarized varieties and Yao varieties by the work of, I guess, Yao in both of these cases and Albin in one of these two cases. But then for the third class of varieties that I'm primarily interested in today, it turns out that these Kähler-Einstein metrics do not always exist. So if you're familiar with complex geometry, it turns out that if you look at complex projective space, CPN, then the first Kähler metric you'll learn about in a complex geometry class, the Fubini-Studi metric, is going to be Kähler-Einstein. But if you look at other Fano varieties, such as if you take CPN and then blow up a point, then it turns out that those do not have Kähler-Einstein metrics. Okay, so now that we're talking about Kähler-Einstein metrics, I want to go back to something sort of algebraic, because as an algebraic geometer, I want to understand things algebraically. So it turns out there's this notion called Kstability that was introduced by Tien to characterize when a Fano variety admits a Kähler-Einstein metric. And this notion was reformulated by Donaldson just a little over a few years after that. And Donaldson's reformulation of this notion of Kstability was purely algebraic and also vastly generalized Tien's earlier definition. And this notion, I won't define it precisely right now, but essentially you can define whether or not Fano variety is Kstable, and what you look at is you look at some degenerations of that Fano variety over the complex numbers, and you associate some invariance to those degenerations. So it's a celebrated theorem of Chen, Donaldson, and Sun, I guess, who are or were at Stony Brook, and also there are results of this by Tien that says a Fano variety admits a Kähler-Einstein metric if and only if it is Kstable. So let me just briefly mention that this was an extremely challenging result in complex differential geometry that was achieved after many years of work. And this is what Chen, Donaldson, Sun won the Veblen Prize for. And the wonderful thing about this theorem is it says that the existence of a Kähler-Einstein metric, which is something in differential geometry, can be detected purely algebraically. So it turns out that if we now just look at these, this nice class of Fano varieties, which are called Kstable Fano varieties, they have a nice moduli theory. So there's a theorem that says that there exists a projective moduli space parameterizing smoothable Kstable Fano varieties of fixed dimension. So this is due to Odaka and Li Wang and Xu, and the projectivity was more recently proved. So at the end of the day, we have some nice theory of moduli spaces for Fano varieties if we restrict to the Kstable ones. And I think maybe from my perspective, this is a lacking of the theorem, but maybe to other people, people would think this is a great thing. But the proof of this theorem, while it's a purely algebraic statement, its proof heavily relies on differential geometry input, especially the work of Donaldson Sun, Chen Donaldson Sun, Spati Sun Yao, and others. So from my perspective and other people in algebraic geometry, we wanted to understand this theorem purely algebraically. So currently, we can't prove this exact statement purely algebraically, but there are many things that we can do algebraically. So maybe I'll state one theorem to end my talk about a purely algebraic statement we can prove about these moduli spaces. So there's a theorem, and I'm citing it to myself and my co-author, Chenyang Xu, as well as Li Wang Xu and Spati Sun Yao, even though in the second and third papers, this was proved algebraically and for, I guess, a slightly smaller class of varieties. But what this theorem says is that if you want to construct moduli spaces of Kstable Fano varieties, your moduli space is going to be Hausdorff. So precisely it says if you have a pointed curve and two families of Fano varieties, x to c and x prime to c, that are isomorphic away from the special point, and you assume that the fibers over 0 are Kstable, then the two fibers over 0 are actually isomorphic. So the limit as t goes to 0 is going to be unique. So the proof of this theorem with Chenyang Xu is purely algebraic, and I think it's not very surprising that this theorem that was proved using very deep results in complex differential geometry, you won't necessarily be able to give an easy algebraic proof of this, but the algebraic proof of this relies heavily on very powerful tools from birational algebraic geometry. And there are other types of similar statements that you can make about constructing these moduli spaces algebraically. Due not simply to myself, but there's many people working on this. So I'll end my talk there. Thank you for your attention.